All right, we are live. Okay, so we are going to go to our 7.4 page. And we're going to start with, well, we're going to start with a little bit of wordiness. We're going to start with some definitions. And let's see, where are my definitions here? Okay, can everybody turn to that page, please? What did I do with my page that I was looking at earlier? No. Oh well. We'll wing it. If I write different words this time than I did last time, it's not a big deal, I guess. Okay, so. You know what? I don't think I even need any words for key terms reciprocal function. That's it. A reciprocal function is you take a function and you divide it into one. That's what reciprocal means. A lot of you, I'm sure, think that reciprocal means just flip over fractions. And yeah, that's kind of true, but that's not really technically its definition. If you take the fraction you're not write this down. If you take the fraction 2/3 and you turn it into its reciprocal, you get 3/2. But really what you actually did was you divided 2/3 into 1. And that's where you learn that that's the same thing. Dividing like that is the same as multiplying by the reciprocal. So that's why a reciprocal function is take the function and divide it into 1. Okay, so there we go. Next, asymptote. We've probably seen this word a few times in the course. We've seen it before, I'm sure. Any ideas what it means, actually? An asymptote is a value, or actually, no, let's make that a line. A line that a curve gets closer to, I should even say, to infinity, but can't touch. You can get infinitely close to the line, but you can't touch it. That's the definition of an asymptote. A vertical asymptote, of course, means that it's a line that goes up and down. But in the case of a reciprocal function, in a reciprocal function, actually, I'll just add it. In a reciprocal rational function, vertical asymptotes are the NPVs. Do we remember what NPV stands for from a couple chapters ago? The non-permissible values of the denominator. Horizontal asymptotes are the values that y can't equal when in the form y equals 1 over f of x. And for both of these things, vertical and horizontal asymptotes, maybe make this as a note somewhere else. Up here we got room. Asymptotes are lines. So remember when we were doing quadratics and I told you that you'd lose half a mark if I asked you, hey, what's the axis of symmetry? And you said, the axis of symmetry is 2. No, it isn't. The axis of symmetry is x equals 2 because it's a line. It has to have some sort of variable. So asymptotes are lines. So a horizontal asymptote is always going to be y equals something, some number. I'll just put a number symbol. And a vertical asymptote is always going to be x equals some number. If I ask you for a horizontal or vertical asymptote and you just give me a number, you don't give me x equals or y equals, that's going to cost you half a mark. Okay, we've already talked about what invariant points are, right? They are points that don't change when an operation is performed on a function. And in this case, the function that we're going to be performing, or the operation we're going to be performing, is reciprocaling it. And I'll ask you to think about it. What are the only two numbers in the entire universe of infinite numbers that you can reciprocal and you still get the same value? I'll check the chat. What are the only two numbers that when you reciprocal them, they don't change? And yep, first person got it right away. It's plus or minus 1. So those are going to be your invariant points. So I'll even write note when y is equal to plus or minus 1, f of x is at an invariant, I hope you can write smaller than me, point. That just leaves approaching the x or y intercept. I don't even know really why that's here, except that maybe we just need to maybe define some terminology or some symbols. Approaching is always going to be equal to, or is always going to be represented by a sideways arrow. So when you are approaching an x or a y intercept, you are actually heading towards a situation where you have basically an asymptote. So for example, if I were to say that as x increases, y approaches 0. And here, let me just kind of cut all that off so that you don't run them together. There we go. If I say as x increases, y approaches 0, I can write that symbolically as x goes to infinity, y goes towards 0. So let's get used to that kind of writing, because you're going to see it quite a bit from now on. And we're going to see it next semester a lot when we do calculus. Okay, I like this. They got a little 5-step way to make graphs of reciprocals. There's actually a couple little things I'd change about it, though. Step 1, lightly sketch the original graph. You could, I guess. I prefer, though, since I want a sketch of the reciprocal, I don't really want to sort of notice that much the original graph that made it. I prefer, instead of a lightly sketched original line, I kind of prefer, let the dotted line equal the things that aren't really my graph. So I tend to go with a dotted line there. Now, asymptotes always have to be dotted lines too, so I hope that doesn't get confusing. Feel free to use more than one color if you want. Another thing I would never ever do is this step 2. Put an x on the graph where y is 1 and -1. It's a graph. Do you actually put little x's in your graphs? No. Put a dot. For heaven's sakes, don't put x's on graphs. Unless you're labeling the x-axis. In which case, there we go. Dot. Solve for the x values to get exact points. Use this to anchor your graph. Determine any non-permissibles, and draw in the curve. Okay, I think we're ready to do some graphing. I feel good about this. Let's do some graphing. Oh, first we have a couple little questions to answer. A line that a curve approaches that never touches is called and we already know this, an asymptote. Points that remain unchanged through a transformation are called invariant points. And fill this out after you draw the graph of 1 over x. So we actually have to go to the next page and draw a graph and then hit this. Okay, this is really dumb because I can't have my chart and your graph on the screen at the same time. So I'm going to get all fancy like here. I'm going to just really quickly flip this over. I did this morning too, and it actually worked really well. I'm going to, oh no, I'm going to take a snip. Snip, I says. I want a new snip, I don't want that snip. And we'll take a snip of this diagram. And we'll go edit, copy. We'll shrink that. And then we'll go up to say here, and we'll paste it in. And we'll just hold it. paste. There we go. And let's see, now we want to move it, so we want to move it. Okay, we want the whole thing and we want to move it up. Come on, come on. There we go, come on, move up. This worked so good this morning. I don't know why it doesn't want to move the way I want it to move. Is it helpful if I did that? No. Any ideas what I'm doing wrong? I'm pushing on the thing. That's just making it bigger. Any ideas how you drag things? Anybody with more experience on tablets than me? There we go. Why won't it go where I want it to? It's not going above that picture, which is unfortunate. I want it to go on top of that picture. So there's got to be a way to change the settings of that. Maybe if I hold long enough, it'll give me some options. There we go. Set picture as background. No, I want the exact opposite. I want it on top. Picture. Keyboard resize. Flip forward. No, I don't want any of that. Let's see, what else can I? What else does it give me? No, I don't want any of that stuff. Oh well, I don't know what to do here. This is not doing what it did this morning. I don't know what I'm doing different. This is exactly what I did this morning. So I'm just going to move it to the side. Come on. Okay, maybe if I just flipped it over, that would help. Oh, still doesn't do what I want it to do. What if I shrunk it and then tried to move it? Would it move better if it was shrunk? Nope. Oh well. Okay, I guess we'll just have no choice but to actually, what if I just go to right here, paste? No, that still puts it down there someplace. Okay, let me just cut that one, delete that one, and we'll delete that one since it's not doing what I want it to do. One more try. I want it right there. Paste. No, it won't put it where I want it. Weird. I don't know why it's not doing that. It did it just fine this morning. Oh well. Okay, we'll just do it the way it is. Okay, so I'm going to use two different colors here, if that's okay with you. I'll make f of x green. So f of x is just x. Y equals x, the simplest graph we can have. So when x is -4, y is -4. When x is -3, y is -3. When x is -1, y is -1. When x is -1/2, y is -1/2, -1/3, -1/4, 0 makes 0. 1/4, 1/3, 1/2, 1, 2, 3, 4. There. Next, g of x. I'll do this one in blue. Okay, g of x is the reciprocal of f of x, or the reciprocal of x, same thing. So the reciprocal of -4 is -1/4. Click on the center drag. I was trying that, it didn't work. The reciprocal of -3 is -1/3, so -1/2. And here's why this one's bold. This one's special. The reciprocal of -1 is itself. There's my invariant point. The reciprocal of -1/2 is -2, then -3, then -4. And then what happens here? Quick, who knows the reciprocal of 0? The reciprocal of 0 is not 0. Because again, what does reciprocal mean? It means divide into 1. Can I divide 1 by 0? I can't divide anything by 0. So the reciprocal of 0 is not defined. It's undefined, which makes it an asymptote. We'll put that down in a minute. So the reciprocal of 1/4 is 4, the reciprocal of 1/3 is 3, the reciprocal of 1/2 is 2, the reciprocal of 1 is itself, again, my other invariant point. And the reciprocal of 2 is 1/2, the reciprocal of 3 is 1/3, the reciprocal of 4 is 1/4. I think I'm ready to graph. Let's go back to the green line. The green line is y equals x, or x equals f of x. So it goes through 0, 0, and 1, 1, and 2, 2, and 3, 3, and 4, 4. and it goes through -1, -1, -2, -2, -3, -3, -4, meow, and there we go. Simple, easiest diagonal line kind of thing, right? 1 divided by 0 is not allowed. So, what does the blue graph look like? Well, I can't ever touch the line y equals 0. Or sorry, x equals 0. X can't be 0. I can't touch the line x equals 0. I'm going to make this a little fatter. Maybe that. So that means that we can't touch the y-axis. So the y-axis is an asymptote. This is the line x equals 0. And we can't touch it because it's undefined. If this was the 90s, back when my beginning of my career, I'd be singing "You Can't Touch This" by Hammer, MC Hammer. Okay, so next, now what? Let's put the invariant points down. The invariant points didn't change. When y was 1 on the first graph, it'll be 1 on the second graph. When y was -1 on the first graph, it'll be -1 on the second graph. Okay, this pen's too fat now. So now, what does the rest of the graph look like? Well, let's see. Let's take some points. When x was -4, y was -1/4. So at -4, we have, when x is -4, y is -1/4, which is, I don't know, like half of this square, right? Because those squares are halves, half of a half's a quarter. I don't even want to try to mess with thirds. When x was -2, y was -1/2. When x was -1/2, y was -2. When x was -1/4, y was -4. That seems to be making this curve. There it is. All right, let's do the other side. When x was 1/4, y was 4. There. When x was 1/2, y was 2. When x was 2, y was 1/2. And when x was 4, y was 1/4. So that's this curve. And that's it. That strange looking thing is a reciprocal graph. This blue thing is y equals 1 over f of x if f of x is a straight line. Okay, so now let's go back to the page before and fill out, let's look at it for a sec, bathe in its glory. Love the fact that I almost missed this biggest dot on the page when I was drawing my line. And let's jump back now and see if we can describe its characteristics. So for the graphs, when we have y equals x, what's the domain? So what was the domain of the green line? Well, it's going forever in both directions. So I can say x is any real number. What's the range of the green line? Same deal. What's the end behavior, which also means the equations of the asymptotes, if any. But here's how I like to describe end behavior. What's it doing towards the ends of the graph? And that's, of course, to the left and right. So, on my green line, if we go to the end, we keep going this way. See the arrow here? We keep going forever to the end, to infinity and beyond. What's going to happen? Well, I would describe it this way. As x approaches infinity, y approaches infinity. And what happens if you go forever to the left? As x goes to negative infinity, y goes to negative infinity. What's the behavior of this graph at x equals 0? Well, in this case, y would equal 0. And what are my invariant points that are shared by both? Well, we already kind of know, right? Where are the 2 points where these two graphs meet? They happen to be 1, 1 and -1, -1. So 1, 1 and -1, -1 are my invariant points. Now, let's do the other one. What's the domain of the green lines? Well, or sorry, the blue lines. The blue lines, what's the domain? Well, actually, x will actually touch every number in the whole universe. All real numbers, except for one. It'll get infinitely close, but it'll never actually make it to 0. It'll get infinitely close. It's really a strange idea. We're getting closer and closer, but we'll never actually reach it. If you zoom in, you'll actually zoom in. You'll eventually always have a little bit of space between those two lines. Right? Even if you zoom in way beyond the subatomic particle level. If you zoom in, if you go up towards infinity forever, you can still zoom in. You'll have to zoom in so small, you're actually smaller than the distance between the nucleus of an atom and its first shell of electrons, for all you chem fans. There is no scale at which we couldn't find some space between those two things. So, how do I describe that? Well, we would say that my domain is that x cannot equal 0, but it can be everything else. If you prefer interval notation, you'd say you can go from negative infinity to 0, but notice it's a curved bracket, which means you can't be 0. And you can go from 0 to infinity, but you can't actually be 0. I kind of prefer set notation for this stuff, but if you like this better, go right ahead. Range, same deal. The only number that you can't get is 0, but it can be everything else. You need to look back at the graph to kind of see that, right? Where is y equals 0? Y equals 0 is actually, let's use a different color. Let's use red. It's actually the x-axis. Why will we never touch the x-axis? I mean, I get it. Y equals 1 over x. X can't be 0. Why can't y be 0? Well, ask yourself this question. 1 divided by something. Is there any possible way to do that division? Is there any possible number I could put in for x and y would be 0? And the answer is no. So that means I have a horizontal asymptote of y equals 0, so that means y can't be 0. Now my end behavior, is this the same? What happens as x approaches infinity? So as I go forever on the blue line this way, forever, what's happening? I would say y approaches 0. And as x approaches negative infinity, y also approaches 0. My behavior at x equals 0, undefined. So you could even say asymptote. There. We filled in the chart. Maybe now is a good time to maybe slow down for a sec, see if anybody has any questions. Can we switch the order of writing domains and ranges? I don't know what you mean by switch. Oh, as in put, do you mean put this first? No, don't do that. Always put the other part first. What x can or can't be specifically, followed by x is an element of reals. Okay? If that's what your question was, Ken? All right. Next. Okay, we did that page. Let's do another one. Consider the following, says Bill Nye. F of x is equal to 2x plus 5. All right, what does that look like when we draw it, and then it's reciprocal? Once again, I'm going to draw this one in blue, and then I'm going to draw the reciprocal in, wait, I'm messing up my order here, right? Last time I did this one in green. This one's going to be green, and the other one's going to be blue. So in green, what does 2x plus 5 look like? Well, it has a plus 5 for a y-intercept, and then you go up 2 over 1, up 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. I think that's lots of points, don't you? Oh, apparently I was wrong. Oh! Well, I'm going to make more points then. Need more points. Oop, I missed that one. Make a bigger dot. There we go. So there's my graph. Actually, I really don't like that section of it. Oh! Keep erase. That's how the eraser works, I guess. Just you touch the line and it erases the entire line. There we go. That's a bit better. Now, the blue line. What does its reciprocal look like? Okay, remember those 5 steps from a couple of pages ago? Me neither. Step one, let's put in the asymptote. So let's see. Y equals 1 over 2x minus 5. So the reciprocal of the green line. Well, what can x not be? Well, the denominator can't be 0. So if I'm looking for what now is my vertical asymptote. I'm already tired of writing that word, so feel free to just abbreviate it. So my vertical asymptote is, let's add 5 to both sides. Let's divide both sides by 2. And there we go. 2.5. Wait a minute, was it minus? Oh, it was plus. Sorry. Plus, minus, minus. That's better. I'm looking at my graph going, that's not the x-intercept. So that's the x-intercept of the green line, which happens to be the asymptote of what's going to be my new, I'll use black, my black line. Because you can't divide by 0. So this is my vertical asymptote. That's the line we can't touch. Okay, do we have a horizontal asymptote? Yes. What's the horizontal asymptote? Well, again, y equals 1 divided by something. Can 1 divided by anything ever be 0, no matter what it is? Nope. So y equals 0, which is, of course, the x-axis. So I'll just maybe make a little fatter line here. So we can't touch that line either. There we go. So what does that leave us? What does this graph look like? Well, we already kind of know it's going to be those 2 curvy arms. So what other point do we know? Oh, yes, we want to know our, and I'm kind of out of room here, sorry. I want to know my invariant points. How do we find the invariant points? Well, the invariant points happen when y is plus or minus 1. So go to the original equation. Remember, the original equation was y equals 2x plus 5. And find out how much x is when y is 1. Minus 5 from both sides is negative 4. Negative 4 divided by 2 is negative 2. So there's one of them. When x is negative 2, so I should maybe put it in coordinate form, right? When x is negative 2 and y is 1, I have an invariant point. Let's see if we can find that. Negative 2 and positive 1. That one right there. Let's find the other invariant point. When y is equal to negative 1, which means that I have negative 1y is equal to 2x plus 5. Minus 5 from both sides. Divide both sides by 2. And I have the point negative 3, negative 1. Let's see if we can find that point. Negative 1, negative 2, negative 3. And there it is. Now, what does this look like again? Well, it's those arms. And what do I know about those arms? Oh, yeah. As I go higher, they get closer and closer, but can't touch that asymptote. And as we go this way, it curves, changes direction, but does the same thing. It gets closer and closer to the x-axis, but can't touch it. Now, what do you notice about this graph that's kind of different than the last one? Can you see what's kind of different about it? Notice that there seems to be a little more crowding here, like it's closer to the x-axis and closer to its asymptote. Like it's a sharper turn around this corner than my last graph was. Now part of it is, this is a little deceptive, this graph is written on a different scale. There's a little more room given, right? This counts from 1 to 4, and in the same distance on that one, we count all the way to 10. So that's part of it, but that's not the only part of it. Let's play with Desmos for a minute. And let's remind you, or let's point out something that I hope most of you would have recognized already. There's patterns to this stuff. Desmos. Okay, oh, look at that. I was just doing that this morning. There's 1 over x, right? There it is, graphed. Okay, before we play with 1 over x, let's play with other stuff. Suppose I ask you what happens when y is equal to x squared, right? There's y equals x squared. What would happen to that graph if I rewrote it, and we've gone through this before. This is not news to us. And we were to say add 1 to it. Or no, let's add a bigger number. What happens if we add 3? Okay, when I turn that back on, what's going to change about the graph? Who remembers how this works? What will change when I turn that graph on? What is the difference between y equals x squared and y equals x squared plus 3? The y-intercept is different. Yep, you're right. It's like we picked up the graph and shifted it from a y-intercept of 0 up to a y-intercept of 3. It shifts up. And if we were to put a plus 3 in here, I'll turn it off again. If I were to put a plus 3 in there, what's going to happen to the graph now when I turn it on? Which way is it going to shift? 3 to the left. That is exactly right. You know what? Good job this morning. A whole bunch of people said 3 to the right. No, it won't. It's 3 to the left. Opposite rule on that one, just like we learned in class. And notice, that would also be true of parabolas. These are parabolas. That'll also be true of the things we just did earlier this chapter, absolute value. Right? What's the difference between this, right? Okay, let me turn off the parabolas. I said turn off the parabolas. There we go. What's the difference between that and what's going to happen when I go plus 3? It's going to shift up. What happens when I put a 3 in this bracket, a plus 3? It shifts to the left. So if that makes sense to you, why should this guy be any different? So there's that. What's going to happen to this thing when I add 3? Now, when I say it shifts to the right, try to imagine not only do those arms shift, but the lines that they can't touch shift with them. So, bloop, it went up 3. On my purple graph, go away for a sec. On my purple graph, I can't touch the x-axis. On the new graph, I can't touch the line when when y is 3. And it makes sense. You can't touch the line when y is 3 because there's no way to make 1 divided by x 0. So if this thing can't ever be 0, y can't ever be 3. Now, let's go back. Let's get rid of this 3. And there's my original. What happens if I put a plus 3 here? Any guesses as to what's going to happen? You pattern recognizers, you. It is going to go left 3. Let's see if that makes sense. There it is. So in other words, the y-axis used to be an asymptote, and now the line x is negative 3 is an asymptote, right? How come? Because negative 3 is my non-permissible value now. Ho-ho! Now, let's do one more little thing to kind of check things out here. Do you remember what putting a 2 here does? Makes it skinnier, and 3, and 4, and 5, and 6, and 7, and 8, and 9, 9, 9. Ah! Super skinny parabolas. And notice that's exactly what happens to my absolute values too. Right? If I have an absolute value graph here, and I put another 3 on it, it gets skinnier. If I put, how would I make it wider? Do you remember how to make it wider? What kind of a number would I have to put where the flashing cursor is to make that a wider graph? Yeah, put in a fraction. So how about 0.2? There we go. Oh, look at that. It's super wide now. Okay, good. You get the idea. So with that in mind, remember that this is 1 over x, right? Like that. What if we had 1 over, and we kind of already saw this, 1 over 2x. What will be the difference? Can you picture that? Well, you kind of already saw it, right? The one we just graphed on the notes there was 2x plus 5. All the 5 did was shift us to the left. What did the 2 do? It kind of made it skinnier, narrower. And if you kind of think about it, that's what it did to the other things too. It made the y values get closer to the y-axis, or at least closer faster as you moved along x. So the bigger this number down here is, the skinnier and skinnier and skinnier. By the time we're at 9, look at that, it almost looks like a right angle. Here, let's put a 99. There, that definitely looks like a right angle. But if I zoomed in, zoom in, see, look at that. It's still the same old curve. Just have to zoom in to see it. Okay, cool. So that's that one. Now, just out of curiosity, what if instead of the 2 down there, what if it was a 2 up here? Any guesses? I'm looking at the chat, waiting for a guess. Hoping everybody isn't asleep. Wider, and you're exactly right, it's wider. Watch. And again, the bigger this number is, 3, 4, 5, 6, 7, 99. I'm going to have to zoom out to even see that. There they are. There it is. It gets wider, it gets further away. Not sharper, the opposite of sharper. Although sharpness is kind of illusory. Illusionary? Illusory. It's an illusion. It's really only sharper looking in there because we're looking at it at a different scale. The logical way to explain it is it gets further from the axes, further from the origin of the graph. Okay, let's go back to notes now that we've had that nice little diversion of looking at Desmos. And let's do one more example. Consider, in fact, why don't you try it? Okay, I'll pause the video and give you a couple minutes to try this on yourself. Unpause. We're recording again. Yay. Okay, let's see if I can catch up to you. First, I will graph y equals 3x. Close that. First, I will add y equals 3x minus 9. And I'll do it in green. So y equals 3x minus 9 is this green line here. It has a y-intercept of 9. It has a slope of up 1, 2, 3 over 1, 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 1, 2, 3 over 1. And there we go. And I'm going to try to make this a very nice, smooth... Ah! Jinxed myself. Very nice, smooth line. Oh, I don't mind that. That was pretty good. I'll take that. Okay, so there's the first graph. Now, in black, we want to actually graph y is the reciprocal of this thing. So what do we need first of all? How about first we'll do our vertical asymptote. And again, I'm tired of writing those words, so feel free to, feel free to abbreviate. Vertical asymptotes happen when I let the denominator be 0 because the denominator can't be 0. So 3x equals 9 and x is equal to 3. So I can't have 3, which by the way just so happens to be where the original graph had its x-intercept. That is not a coincidence. For my horizontal asymptotes, horacy, I need to find out, or I need to just sort of logically reason out, what can y not be? Well, obviously, y can't be 0. And y equals 0 is the x-axis. There we go. So there's the 2 lines our graph can't touch. Let's find now our invariant points. Invariant points happen when y is 1. So 1 equals 3x minus 9, which means 10 is equal to 3x, which means x is going to be 10 thirds. That's 3 1/3, or when x is 3 1/3, y is 1. So when x is 3 1/3, now I actually don't bother looking for that too much. I just kind of go to, oh, here's where y is 1. There, does that look like 3 1/3 to you? I'm sure it is. Yeah, it's pretty close, eh? 1, 2, 3 1/3. Yeah, I'll take that. So there's one invariant point. My other invariant point happens when y is negative 1. And that would be an 8. Just go goof that up. And so when x is 8 thirds, y is negative 1. And that looks pretty good. Negative 1's about here. Yeah, 8 thirds, right? Almost 3, 2 2/3. And even more so than the last one I drew, this guy heads to the y-axis super fast. Very sharp. Almost turns at a right turn at that dot. So something like that. Something like that. By the time I'm at 5, there'd be so little room between the line I'm drawing and the asymptote that it can't touch that they would almost look like they're on top of each other. But of course, we know that in reality, they don't touch. They cannot touch. Super cool stuff. I like these. So anyway, I'm I'm going to stop there. That's going to be it for today's lesson. We'll pick it up there tomorrow, and we'll talk about quadratics. I always split this lesson into two classes. As you can see, we did answer some questions at the beginning, but for the most part, this is like a 40-minute lesson. This is complicated stuff to try to explain, so it takes time. So we'll give tomorrow's class, we'll give you some room to breathe to do quadratics, which is actually even more complicated than this. And while we're at it, okay, I guess I should probably stop the video. That's enough video for today.